to the second lecture of ETC. Today we'll start with intrinsic semiconductor, extrinsic semiconductor and doping. So before starting this, let's just revise about resistivity and conductivity. Okay, so do you remember this formula? Rho L upon A. This is the formula of the resistance. This is resistance and this is resistivity. And resistivity is the property of the material which helps it to oppose the current, right? And conductivity is the opposite of resistivity. What was the unit of this? Okay, let me just break this down for you. Right? L. The unit of resistance is ohm. The unit of area would be this, and the unit of length is centimeter. So I can cancel this. So the unit is right. And what we learned from the last lecture, that as temperature increases, the resistance also increases, the resistivity also increases, because they are the interrelated thing. Now here, what would be the unit? Unit would be mho per centimeter, or also known as Siemens per centimeter, the opposite of this. Now the conductivity can be given as carrier concentration into the charge into the mobility. Since this is kind of fixed, so we can say that the conductivity depends on the carrier concentration and the mobility. So for the metals, yes, since the carrier are mostly electrons, can I write it as N? And this is Q and this is my mu. Are we clear on this? And for semiconductor, what we know, that it is bipolar, right? So what can I write? Conductivity would be N Q and the mobility of electrons plus P Q and mobility of holes. Are we clear? Okay, now tell me, as the, wait a second, let me just change my pen. Yes, so as the temperature increases for the semiconductors, what will happen? The conductivity will also increase, right? I want you to keep this in mind. This is very important. So now let's come to intrinsic, extrinsic and doping. Now this is the most favorite topic of students, and you know, all of you know about this. So if any one of you does not know about this topic, then hello, hi, good morning. I made this video especially for you. So what is intrinsic semiconductor? Well, you just have to remember one word, that is pure. What is intrinsic? Pure. What is intrinsic? Pure. Pure. So what was happening, that this intrinsic semiconductor was very pure and the conductivity was less for this. And what do we want from semiconductors? We want that the conductivity should increase, right? So what we did was, to this pure semiconductor we added some impurities. Right? And what it gave us? It gave us extrinsic semiconductor. Impurities are very bad, but not in the case of semiconductors. And this, the conductivity of this was good. It got some very good electrical properties. So it has very good uses, right? Pure intrinsic semiconductor, we added some impurities and it gave us extrinsic semiconductor. Now these impurities are also known as dopants. Okay, it goes with both the names. So what we can say, that this extrinsic semiconductor, this is, let me just drop the line. This is a doped semiconductor. Yes, this is an impurity semiconductor. This is an artificial semiconductor, because we think that this is natural, so this has to be artificial. And this is also known as degenerated. It can go with any name, that's why I'm writing all the names so that you don't get confused in exam. And it is also known as compensated semiconductor. Why? Because we are compensating them with dopants. Okay. So for the intrinsic semiconductor, do you remember this formula we just learned? Yes, you do. And for the intrinsic, what happens is N and P are equal, which is, I can write as Ni. This is the intrinsic carrier concentration. So can I write is it as like this? NQ, I'm taking it common, mu N plus mu P. And for the resistivity, I'll just take its reciprocal. Right, this was the unit. And I can write it as NIQ upon mu plus mu P. So why we are doing the doping at the first place? Because the value of current was very low for the intrinsic semiconductor. This is the formula which you need to remember for the intrinsic one. Now let's move on to the extrinsic semiconductor. Now we can make any intrinsic semiconductor into extrinsic by adding two types of impurities. One is trivalent impurities and other is pentavalent impurities. Okay, so if we are adding trivalent impurities, this will make it p-type semiconductor. And if I am adding pentavalent impurity, this will make it n-type semiconductor. Now, in a p-type semiconductor, the holes are the majority charge carriers. And the electrons are minority carriers. And opposite is the case for n-type. Here electrons are majority carriers and the holes are minority carriers. You can learn it from the name itself. Whatever the name is, that is the majority charge carrier. N is associated with electrons and P is associated with the holes. So I think it will be easy for you to remember this. Okay, so let's move ahead. So the formula for conductivity was like this: N Q mu N plus P Q mu P. Right. So for the N type, this is almost negligible. So can I put it like 0? And this is ND or the donor. This becomes donor because this has donor atoms, mu N. Now there is a long theory behind it, but it will not come in the GATE exam, so I'm skipping it because we have a limited time. But if you want to know it, I can, there is like such kind of diagrams which everybody will explain you and will waste your time, but trust me, this will not come in exams, so that's why I'm not going much into it. So what happens is these are the covalent bonds. Similarly, yes, something like this. So what happens is, due to doping, we get an extra electron over here, which contributes to the conductivity. And similarly, similarly happens for the holes, that we get an extra hole. But this is all extra thing, you can always read it in the books. So we are concerned with the formula. Similarly, for the P type, same formula. Now you know what will cancel out. We have studied this a lot. This will cancel out and this will be N, A, Q, mu, P. And what are these? These are the acceptor atoms. And what were these? These were the donor atoms. Okay, so we are pretty much done with doping. I did this topic very slowly and very calmly because this is a very important topic. Questions are repeated in GATE exam year after year. That's why I took it very slow. So now let's move on to the next topic. So about this, we know that subject is full of theory and it has lengthy definitions, and in the coming lectures when we will study about these semiconductor devices, it will have big diagrams, right? So what I do is I skip the writing part, and I will skip the writing part because I feel that it is a waste of time, that I'm writing lengthy lines here rather than, I think that I should more focus on explaining the topic. I'm trying to save you from the theory because we are here strictly doing the GATE syllabus and we are not learning theory. We are learning what will come in the exam. But, this is entirely my opinion. I want to know your opinion on this, that whether you want me to write along with you or you want me to keep as it is going. Because it won't affect anything for me. I'll still cover 4 to 5 topics in a video, but the length of the video will stretch to like 45 or 1 hour. In fact, now I'm trimming the part, like this writing part, I trimmed it so that, we don't waste time. So just pause the video and post your opinion because it is very important for me to know that whether you want me to skip the big writing and drawing part or you want to write along. Okay, so now that we are done with the pep talk, note down this table or take a screenshot. Now let's do some GATE questions. This question was asked in GATE 1995 for 1 mark. Let me write it here. GATE 1995. Okay, so the solution is, we know that by the mass action law, what was the formula? N into P is Ni square. This was the formula. Right, so the P is given. P for the silicon semiconductor is given 10 to the power 15. And Intrinsic carrier concentration is given 1.5. We simply have to put this in the formula. Yes, so if I do it, let me just do it quickly. 2.25 into 10 to the power 15. I think this would be also 2.25, right? So this is very easy. Just have to put the values in the formula. So what is the answer? The answer is C. So the next question, a heavily doped N-type semiconductor has following data: hole to electron ratio is 0.4. The doping concentration is 4.2 into 10 to the power 8 atoms per meter cube. The intrinsic concentration is 1.5 into 10 to the power 4 atoms per meter cube. The ratio of conductance of the N-type semiconductor to that of the intrinsic semiconductor of the same material at the same temperature is given by, and these are our options. So the solution is pretty easy. Yes, we know all the formulas. The conductivity formula for the intrinsic was Ni. Yes, you're writing in your notebook. Q mu n plus mu p. That's right. And for n, I can write n mu n and q. So we have to take the ratio. Can I write it here? Yes. Into Ni. I'm just cancelling the q's. This will be mu n plus mu p. Now I'm putting the values power 8 and I'm keeping this as it is because I'm about to take this common from the denominator. Mu n, and this is 1 plus mu p and mu n. We are like kind of cancelling both of them. So if I put the values again, and this 1.5, and this ratio will come out to be, this whole thing will come out to be 1.4, I guess. Yes, so the answer is 2 into 10 to the power 4, which is D. So do you see, this question came for 2 marks. So in EDC, the important thing is that you have to remember the formulas, and the questions are quite simple. So this question was asked in GATE 2016, and the question is: a silicon sample is uniformly doped with donor type impurities with a concentration of 10 to the power 16 per centimeter cube. The electron and hole mobilities in the sample are 1200 centimeter square per volt second and 400 centimeter square per volt second respectively. Assume complete ionization of impurities. The charge of an electron is 1.6 into 10 to the power minus 19 coulomb. They have given this, but you should know it by your own also. The resistivity in the unit ohms per ohm centimeter is. So this is, we have done this also in the starting of the video. Resistivity is the reciprocal of conductivity. And what is the conductivity here? See, it's this. Can I write it like this? Yes, because this is the formula. So let me put all the values. What is this? 10 to the power 16. Okay, we should already know this, right? and so the answer will be 0.52. So this question was asked in GATE 2003. The intrinsic carrier concentration of silicon sample at 300 Kelvin is 1.5 into 10 to the power 16 per meter cube. If after doping the number of majority charge carriers is 5 into 10 to the power 20 per meter cube, the minority carrier density is. So Ni is given and N is also given. Right, so both of them are given. So this is a homework problem because this is very easy. I don't want to solve it. I've done similar questions just now. So post the answer below and let me know what is the correct answer. Okay, so that's all for this lecture. If you have any problem, you can mail me. My mail ID is mentioned below. Okay, so what we did today, let's see. So today we studied about resistivity, conductivity, its formulas, intrinsic semiconductor, extrinsic semiconductor. We studied about doping. We learned about N-type, P-type, acceptor ion, donor ion, pentavalent impurities, tetravalent, trivalent impurities. And we also wrote the electrical properties of germanium and silicon. I cannot explain much in this because this you have to learn it. So take a screenshot of this electrical properties or note it down because this is something which you should remember. And then we did couple of GATE questions. One problem I gave you homework to which you have to post the answer right now because that's a very easy problem. In the next video we'll do the law of electrical neutrality, which is left, which is a part of doping. Then we will do Fermi energy, Fermi level, and then with the related concepts. So that's all for this video and see you in the next one.